Good morning, dear students.
Morning, sir.
Good morning, sir.
Good morning, sir.
In electrochemistry, we were discussing the batteries. We have seen primary and secondary batteries. Leclan cell, mercury battery, or mercury cell are primary batteries. So, which are use and throw kind of batteries where cell reaction will be irreversible. That's why they can't be recharged. Once the products are formed, that's all. Whereas secondary batteries are those which can be used by recharging them, where cell reaction is reversible. So we have seen lead storage battery and nickel cadmium battery. So after that, we have one example to study under fuel cell. Okay. So you would have, if you know about recent automobile developments, hydrogen fuel cells are often of high demand now. Okay. So we'll see what is this hydrogen fuel cell itself in our syllabus. Okay. So hydrogen fuel cell. Thoughts? So this is fuel cell. Okay. So fuel cell, as the name itself suggests, it's a voltaic cell. Basically, it's a voltaic cell. In what way it is different from normal voltaic cell to this and this? The fuel cell will utilize a fuel, and that fuel will be subjected for combustion, and the energy liberated by combustion will be converted to electrical energy. That's the only thing. So combustion takes place here. In the previous case, there was oxidation and reduction at anode and cathode. So which used to generate electrons and migrate, and thus electric current used to generate. Here, a particular fuel will be used. A particular fuel will be combusted, which whose energy will be converted to chemical energy. So basically, here also chemical energy to electrical energy. That's why these fuel cells are also voltaic cells. But we use a particular fuel and burn that one and convert chemical energy to electrical energy. That's the major difference here. Okay. So when I say fuel, I don't go for fuels like petrol, diesel, and all. Here, clean fuels like hydrogen and methane or methyl alcohol, such fuels will be used where it doesn't give out solid residue much. Okay, especially hydrogen, if it is used, it gets completely converted to water. Okay, so how do we therefore give a statement for fuel cell? Okay, it's a voltaic cell. It's a voltaic cell in which energy of combustion of a fuel like H2, methane, methyl alcohol, etc., is converted to electrical energy. Is converted to electrical energy. That's the fuel cell for you. We are going to have one example to study, that is hydrogen fuel cell. So when I say hydrogen fuel cell, it's obvious that hydrogen is the fuel here. Okay. Basically, the fuel cell consists of electrodes. So here electrodes used are carbon rods, perforated carbon rods. These perforated carbon rods are filled with platinum and palladium. Acts as electrodes and filled with platinum or palladium for catalyzing the combustion reaction. Okay, so it has in between there is aqueous electrolyte, which is the KOH solution. Okay, potassium hydroxide alkali solution. It is hot aqueous solution of potassium hydroxide is used as electrolyte here. Okay, so there is anode and cathode, which are perforated rods of carbon instilled with platinum and palladium, which is powdered, and there is aqueous hot KOH solution, which serves as electrolyte. Okay, now we are going to pass hydrogen and oxygen through the inlets. So major reaction that is expected is oxidation of hydrogen to form water. That's all the thing. Okay, so the reaction at anode, as we very well know that anodic oxidation and cathodic reduction, the reactions that take place at anode and cathode, we can write. People have to tell me, between hydrogen and oxygen at anode, which would react first? As we know, anodic oxidation, is it hydrogen that reacts at anode or oxygen? What would you guess? No, since of late non-cooperation, not answering, hydrogen is the one which can undergo a reaction at anode, because hydrogen undergoes reaction at anode, undergoes oxidation to form water. It becomes H plus, loss of electron. So this can be shown like this. There is hydrogen and OH minus ions from the alkali. Okay, so it becomes 4H2O, liberate 4 electrons. This is the reaction that takes place at anode. Okay, how about at cathode? Cathodic reduction. So here O2 will gain electron along with OH minus water to form OH minus ions. So the reaction that takes place is O2 combines with water. Of course, it takes 4 electrons liberated during oxidation. I would say 4 electron, giving rise to 4 OH minus ions. So reduction is taken place. If you see the net reaction, okay, so common terms we shall cancel. 4 electron like this, like remaining is 2H2 plus O2, giving rise to how many water remaining? 2H2. So this is how the reaction takes place. That means hydrogen getting combusted to water. Meanwhile, 4 electrons are liberated during oxidation at anode, and the same electrons are gained during reduction at cathode. So there is electron movement, thus electric current is generated. So this is about the fuel cell, how exactly the combustion of a fuel can generate electric current. Okay, and this fuel cell is a very efficient fuel cell. Why do we say very efficient? Here, the energy liberated by combustion is converted to the electrical energy with a 70% efficiency. And this kind of 70% efficiency is not seen in generation of electric current through any conventional methods. Okay, it may be hydroelectric power generation, or by burning coal they can generate electric current. So in all those cases, around 35, 40, 45% of efficiency would be seen. Remaining energy will be wasted by dissipation. Whereas here in fuel cells, around 70% of the energy obtained by combustion will be converted to electrical energy. So this cell is very efficient. In that way, this cell was used for Apollo space program by NASA. Apollo space program was the third program that launched by NASA uh, to airlift people to the space by the satellites. So this Apollo program, which was the third program of NASA, utilized this fuel cell because they had some advantages also. What is that? If they use hydrogen, it generates electric current, and the product obtained, the byproduct is water, and this water can be purified and can be used as a potable water for drinking purpose. So for astronauts, so there is a double advantage. So in space programs, they only take only those kind of things which can be recycled and which can be consumed back. There cannot be a dustbin and some BBMP can go and collect that one. It's not possible, right? So recycling is what is the priority. So hydrogen, when it is used, water can be utilized for drinking purpose. So that is the thing. So the some of the advantages of this, it is
Where will they
70%
get
efficient.
oxygen, sir? Where will they get the oxygen, sir?
That's they have to carry hydrogen and oxygen. They can't produce, no. They have to carry. Huh? So when they carry hydrogen and oxygen, uh, of course, that is also a fuel for rocket propulsion. Part of it can be utilized for this fuel cell also, right? Okay. So it is 70% efficient. That is one of the major advantage. So here, no residue left. That is one more advantage, and it's a clean energy. Okay, and calorific value of hydrogen is very high, and that's the reason why all automobile manufacturers are looking for hydrogen as a alternative fuel now. For this fossil fuels, petrol and diesel, the alternative energy that we are looking for is the solar energy. But by using solar energy, driving a vehicle is not feasible. Otherwise, it would have come by now. So because solar panels are extensively have to be used uh, so that it can give sufficient energy to drive the vehicle. Uh, Still, whatever the existing technology is there, with that we will not be able to generate so much energy to drive the vehicle. But though experiments are there under progress, however, this hydrogen, if it can be used safely, safety is the major concern with respect to hydrogen. If hydrogen can be used safely for combustion, that becomes the future fuel, and that is, of course, there is almost a success rate. There are companies like Toyota, Hyundai. They've already released their cars based on hydrogen. It is like hydrogen will be combusted in a fuel cell, and electric current will be generated, will be stored, and that will be used for driving the vehicle. And probably in another 5 to 10 years, in India also we can see hydrogen vehicles, and which would be much responsive and doesn't have any side effects of pollutants. So these are all some of the advantages. Okay. So this is fuel cell for you. That's all. Just know about what is anode, cathode, and platinum, palladium, which is instilled there to catalyze the reaction and the reactions. Anode and cathode. That's all. Come on. If it is done, I'll proceed with the last part of electrochemistry, that is products of electrolysis. Is this complete now? Can there be a response for this?
Yes, sir.
Uh,
Yes, sir.
let's proceed now. The last concept that we need to discuss is products of electrolysis. Okay. So when you pass electric current through any electrolyte solution, electrolysis takes place. What is electrolysis? We have stated in the beginning itself. It is the phenomenon of decomposition of a substance into its elements or smaller compounds by passing electric current through its solution or through molten state anyway. Okay, so that is what is products of electrolysis. And we also have seen one point pertaining to this in electrochemical series, the last point, that when you pass electric current through a mixture of ions, based on the knowledge of electrochemical series, we can predict which product will be obtained first. So in that point, we have also mentioned that an ion with high SRP undergoes reduction preferably compared to the ion with lower SRP level. Okay. Similar concepts will be utilized here. So let us predict upon passing electric current through any electrolyte solution, which would be the product at anode and which would be the product at cathode. Fine. So we'll take one simple example to start with. Okay. Electrolysis of molten sodium chloride. When I say molten sodium chloride solid has been melted into liquid. Okay, so NaCl Na plus and Cl minus. It simply dissociates in molten state to give the Na plus cation and Cl minus ion. So when you take only NaCl in the molten state, there will be no more ions as such. So at anode and cathode, what are the reaction that is expected? Let's see. So at anode attracts anion, Cl minus, it would lose its electron and become Cl, liberating electron. So one more Cl combines with this to liberate out a Cl2 gas. So better take 2 Cl minus, Cl2 and 2 electron. So chlorine gas liberates at anode. Then what is the reaction at cathode?
Na plus
So
giving
cathode, Na plus is the ion at the cathode. One second. Na plus gets electron and becomes Na. That's all. This is as plain as this. There are two cations. There are two ions. One is cation, another one is anion, and anode oxidation, cathode reduction. That's all. There is nothing complication in this particular electrolysis of sodium chloride. Whereas when you take electrolysis of aqueous NaCl, that means NaCl solution in water, then there is a issue. What is that exactly? Same NaCl is there in water medium, that's all. But when you pass electric current, the electrolysis takes place to give the products of electrolysis. In case of aqueous NaCl is at anode certainly it is chlorine that liberates. At cathode, we expect sodium, no? Hydrogen liberates. Then why it is happening like this? In molten sodium chloride, at cathode sodium, because Na plus gets reduced, we know NaCl solution contains Na plus cation, it has to be reduced. Same NaCl in aqueous medium liberates chlorine at anode and hydrogen at cathode, not Na plus. Then we need to look into it. So in aqueous NaCl solution, what are all the ions present? Let's see first. Okay. So the first ionization takes place. NaCl dissociates to give Na plus and Cl minus ions in aqueous medium. This is expected. But water is a very weak electrolyte. We know this ionic product of water Kw is equal to 10 raised to minus 40, which is obtained as 10 raised to minus 7 H plus and 10 raised to minus 7 OH minus, which means water dissociates to a very less extent, but however, it will dissociate to give little amount of H plus and OH minus ions for sure, right? So therefore, when water dissociates, it would give little quantity of H plus ions and OH minus ions. So the major difference between electrolysis of NaCl in molten state and aqueous medium is, in molten state there is only two ions, Na plus and Cl minus, whereas in the aqueous medium there are two cations and two anions. So when you dip electrodes and pass electric current, two cations move towards cathode, two anions move towards anode, and there exists a kind of competition between the ions to get reduced and to get oxidized. So in a mixture of cations and anions, which cation will be reduced first and which anion will be oxidized first is the question. So fine, for that we have one important rule to make here. What is that? Among cations, anion with high SRP preferably undergoes reduction. Okay, high SRP reduction among cations. Then how about anions? Among anions, okay, this is not anion, this is anion. Okay, I'll just give it more space. Okay, among anions, the ion with low SRP. When I say low SRP, the oxidation potential, corresponding oxidation potential will be high. Okay, when SRP is low, what does it mean when SRP is low? Potential to undergo reduction is low. If potential to undergo reduction is low, potential to undergo oxidation will be high. As simple as that. So I can say the ion with low SRP, meaning high SOP. The same ion will have high SOP. What is SOP? Standard
oxidation potential.
Oxidation potential.
So among anions, the ion with low SRP, meaning high SOP, undergoes oxidation preferably. Okay, so this is the important statement that you need to know. Cation, when there is a mixture of cations, the ion with high SRP undergoes reduction. In a mixture of anion, the ion with low SRP or high SOP undergoes oxidation, preferably at anode. Okay. So among cations, when I say cathode, the reduction takes place at cathode, the oxidation takes place at anode. Now, coming to these ions, in aqueous medium of NaCl solution, there are two cations and two anions. So when I apply this rule, between Na plus and Cl minus, whichever has high SRP can easily undergo reduction. So you know the knowledge of electrochemical series. So can you tell me, between Na plus and H plus, which one has high SRP? It is hydrogen, Amshu says. So Na plus, we know the series starts with lithium, potassium, sodium, magnesium. And if you observe what kind of metals are there followed, then first the series, electrochemical series, starts with the S block elements, more reactive. Then slowly iron, zinc and all you get. So D block elements. Then there is hydrogen. After hydrogen, again there is D block elements. Those D block elements are least reactive ones, like copper, gold and silver. So further when you move down, there will be P block elements which are reactive. The series ends with reactive elements. So in activity series, the series starts with reactive metals and ends with reactive non-metals, and in between there is moderately reactive or relatively less reactive D block elements present. And at the middle there is hydrogen which separates them. And what is SRP, standard reduction potential of hydrogen? It's
0.
0 volt. It is assumed to be 0. And sodium comes above standard hydrogen electrode. After hydrogen electrode, whatever the metals have placed there, they all have positive SRP. Above SHE, standard hydrogen electrode, the metals placed are the negative SRP. So now tell me, between Na plus and H plus, which one has low SRP?
Na plus.
Na plus. Which one has high SRP?
H plus.
H plus. So in that way, uh, H plus will be preferably reduced at cathode. So between two cations, Na plus and H plus in aqueous NaCl solution, H plus will be preferably reduced at cathode to hydrogen gas. That's why we don't get Na plus, we get H2 gas at cathode. Okay, so let me write this part. Okay. H plus has ISRP. If you want the values, so when you reduce Na plus to Na, the potential that's been found out to be E naught, standard reduction potential, is minus 2.7. Whereas hydrogen reduction will be showing like this, because H plus is obtained from water dissociation, right? So we show from water itself, gets 2 electron, H2 plus 2OH. So SRP of this particular reaction liberating hydrogen is minus 0.41 volt. Why it is not 0? Because we show the entire water here. H plus is purely when reduced, then it is 0 for hydrogen electrode. Since it is aqueous medium, H plus is obtained from water and then get reduced to H2. We have to get from water itself. For this reaction, SRP is minus 0.41 volt. And still 0.41 minus 0.41 volt is the relatively, since it is negative, is high SR. Okay, so what is the conclusion? Important. Therefore, H plus gets reduced at cathode to H2 and not sodium. Sodium remains in the solution. Is that okay? So we found out what is the reason as to why Na plus is not discharged at cathode. Instead, H plus will be discharged as H2 in aqueous NaCl solution, contrary to molten NaCl. In molten NaCl, Na plus is reduced to Na. Metal is obtained. Whereas in aqueous medium, H2 is liberated. We found out the reason. For the reason that Na plus and H plus has ISRP, so that preferably reduces. Now between Cl minus and OH minus, which will be oxidized at anode preferably, is what the discussion now. So can you people guess between Cl minus and OH minus, which can be preferably oxidized? Any idea? Any guess?
Sir, Cl.
Cl minus. Okay. Okay. Let me give the values. Then we can decide on. One second. I'll just write the reaction for this oxidation of Cl minus. Plus 2 electron. I'll give SRP itself. When I give SRP, you have to think in terms of oxidation potential. If SRP is low, SOP will be high, like that. Okay. Or indirectly, you can say low SRP can favor oxidation. Okay. So E naught will be plus 1.36 volt for oxidation of chlorine. And now the oxidation of OH minus ion, again OH minus ion come from water, right? So we represent like this. O2, 4H plus ion plus 4 electrons. E naught for this reaction is plus 1.23 volt. Now tell me, for the oxidation of Cl minus to chlorine and oxidation of water to liberate oxygen at anode, liberating electron, the SRP values have been given. Which is the most probable reaction? Is it liberation of chlorine at anode readily takes place, or liberation of oxygen at anode readily takes place?
Oxygen.
Liberation of oxygen.
Oxygen, because this is low SRP, corresponds to high SOP. Therefore, what is the important conclusion we get? Therefore, so O2 must be liberated by at anode, let's say. O2 must be liberated at anode by the oxidation of OH minus ions, meaning from water itself, right? So that's the thing. Oxygen must be liberated. But which is being liberated? What did I say? Okay. So between this chlorine and this one, okay, I have not concluded here. I'll just write here. Okay. Between Cl minus and OH minus. Okay. So this oxidation of OH minus has low SRP. So we have got it from this. Now, therefore, what is the conclusion? Oxygen must be liberated. But actually, in the experimental setup, when you do this electrolysis of aqueous NaCl solution, we have just concluded that at anode, what is liberated? Chlorine and not oxygen. So there must be a special reason for that. Okay. So what is the reason for as to why the oxygen liberates and not chlorine? Okay. So as per our generalization, any ion with low SRP preferably should undergo oxidation at anode. So as per that, oxygen must be liberated when the aqueous NaCl is electrolyzed. But chlorine is getting liberated. Okay, so I can say this. Liberated at anode, though it has high SRP. The reason behind it is, this is a special case. In most of the cases, our generalization will be working. That is, among anions at anode, the ion with low SRP undergoes oxidation preferably is correct. But especially in case of aqueous NaCl solution, instead of oxygen, chlorine gets liberated. That's a reason for that is the oxygen has something called over voltage. What is over voltage? See, some ions, though they have high SOP or low SRP, they will not be oxidized at anode due to their over voltage, meaning their mobility inside the ion, that means inside the solution, will be very low. The ionic mobility will be very low. That means OH minus ions move slowly when compared to Cl minus ions. So you require little high voltage to make them to move towards anode and get oxidized to oxygen. By then, the chlorine picks up the electron, will move towards the anode and lose the electron and get released as chlorine. So this happens only in those cases where the ions have low mobility in the aqueous medium. Whenever mobility is low, it requires beyond the certain point limit to apply the voltage. That means it requires excess voltage to make them move towards the anode and get oxidized. That is called over voltage. Any ion which has low mobility and thus possesses over voltage will not be preferably oxidized. Instead, the other ion next to it, which has high mobility and low over voltage, will easily get oxidized. So one word we say is oxygen has higher over voltage and it cannot move faster. Therefore, Cl minus will be oxidized. But in all remaining cases where there is no mobility issue, the generalization works correctly. Okay, so O2 has over voltage, that is OH minus ions of water require high voltage to get oxidized as their mobility in aqueous medium is low or is lower than Cl2. I'll say Cl minus. Okay, lower than Cl minus. So otherwise you would have got oxygen itself. So because of this extra factor, the chlorine gets liberated. Now, just finish off writing. We'll take some more examples of products of electrolysis. Let me know if it is complete. So finally, in aqueous solution, at cathode hydrogen liberates due to high SRP. At anode, we expected oxygen to liberate because that has low SRP, but still chlorine gets liberated. That's because of the over voltage of oxygen. For oxygen to be liberated, high voltage is required due to low mobility of the respective ion from which oxygen is obtained. Okay. Is this complete now? Shall I proceed?
Yes, sir.
Okay. So this is about electrolysis of NaCl in molten state and in aqueous solution. Next we'll take up electrolysis of copper sulfate. Of course, in aqueous solution. Okay. You can carry out electrolysis by using any electrodes. Sometimes you can use, graphite electrodes. Sometimes you can use, in case of copper sulfate, you can use both anode and cathode as copper electrodes, copper rods itself, or you can go for platinum electrodes. So when you take these kind of different electrodes, which are used for electrolysis, some electrodes are reactive electrodes. They can take part in the reaction along with the ions because the nature of the electrode is reactive. Whereas some electrodes are, if it is platinum, gold and all, they are noble metals. Even upon passing electric current through them, only ions in the solution would react. They themselves would not involve in the reaction. Okay. So reactive electrodes and non-reactive electrodes. So whenever reactive electrodes are used, the electrodes also take part in the reaction, and thus products will be obtained differently when compared to the case where non-reactive electrodes are used. Because in case of non-reactive electrodes, the electrode material will not take part in the reaction. Okay. This is another important factor. That is, the nature of electrodes used will also decide the products obtained. Okay. Now we'll take up electrolysis of copper sulfate, case A, using copper electrodes. These are reactive electrodes. They can take part in the electrode reaction. That's the meaning. Okay. When you take copper sulfate solution, oh, you tell me copper sulfate when added to aqueous medium, it dissociates to give Cu2 plus, and the anion here is SO42 minus. In case of NaCl, it was Cl minus. Here it is sulfate. Okay. So apart from that, as we know, this water would also give its ions H plus and OH minus. Now there are two cations and two anions. Again, when you pass electric current through the solution using copper anode, copper cathode, competition exists. Now you have to look at all probable reactions at cathode and at anode and decide based on the SRP values. Is that okay? So now we shall take up the reactions at cathode. What are the expected reactions at cathode? See, there is a cathode attracts cation. Which are the cations? Cu2 plus is there, H plus is there. Now Cu2 plus gets electron and will be reduced to copper. This is one reaction. Another reaction is H plus getting reduced to H2. That we show by taking water itself. Giving rise to H2 plus 2OH minus. Okay, it is actually 2 electron, right? Okay, so this is another reaction where hydrogen liberates. Let me write SRP values for these two. Standard reduction potential. This copper we know 0.34 volt. Daniel cell we have used. So E naught of this liberation of hydrogen from water minus 0.41 volt. Okay. Now between the two, these are the two important reactions that can take place. Okay, solution, in the solution Cu2 plus ions can convert to copper, and another liberation of H2 from water. Now between the two, can you people tell me which can be readily taking place? Is it reduction of copper or reduction of water to liberate hydrogen? Which preferably takes place at cathode?
Liberation of water.
Liberation of water.
For cations, you use high SRP or low SRP.
High, sir.
So that means copper gets reduced preferably to the reduction of water to liberate hydrogen. Okay, so in aqueous solution of copper sulfate at cathode, which is the most probable reaction that preferably takes place, it is reduction of copper. Copper gets deposited to the cathode. Hydrogen will not be liberated. You can see here plus 0.34. It is minus. So you have to consider the sign also. So this is low SRP. This is high SRP. So therefore, what we can say, Cu2 plus gets reduced at cathode due to high SRP. For cations, the ion with high SRP will be preferably reduced. Okay. So then we'll take up a anode. Okay. So at anode, what are the probable reactions? Let's see now. So the ions present in the solution is sulfate and OH minus ion. What would happen when sulfate is oxidized? SO4 2 minus. It becomes S2O8, liberating 2 electrons. Okay. P block is over in your college.
Yes, sir.
What is that H2S2O8? Have you come across H2S2O8 and its structure?
Oleum.
Oleum.
That is H2S2O7. Peroxosulfate, we know.
Peroxo acid.
This is peroxosulfate. Okay. E naught for this is plus 2.01 volt. Next is the oxidation of OH minus ion from water, that can be shown like this, liberating 4H plus O2 plus 4 electron. And E naught for this is 1.23 volt. Of course, plus.
We should remember the SRP values, sir. Not values.
Generally, you remember like this, which is low, which is high, like that. In the problems, they generally give. Okay, so whichever has high SRP, low SRP. Otherwise, the data will be given in terms of activity series, that the one is above in the series, below in the series. Such a kind of indirect data will be there. Okay, so these values like copper, zinc, you know already. Copper is plus 0.34, zinc is minus 0.76. Water you remember, that's all. Okay, only during oxidation and reduction. You can see this reduction is minus 0.41. During oxidation, to liberate oxygen, it is plus 1.23. Rest they have to give. Okay, they will give. Apart from these two reactions, that is what we expect, right? This sulfate is there in the ion and OH minus is there in the ion. They both undergo oxidation, and these are the SRP values. Since the electrode used is reactive electrode, at anode, copper also undergoes oxidation. How? Cu from metal rod can be oxidized to Cu2 plus and get into the solution. Cu gets oxidized to Cu2 plus and dissolved into the solution. And here E naught for this would be 0.34 volt. Is it okay? So this is oxidation minus 0.34 volt. Now you have to compare all the probable values and tell me which is the reaction that is preferably taking place at anode in copper sulfate solution.
Copper.
I'm sorry, this is
Copper.
oxidation potential.
Copper.
Let me write reduction potential. For reduction potential of copper, it is 0.34 itself. All are reduction potential.
Copper, sir.
Still copper only, right? So why do you think copper undergoes oxidation preferably?
So because it has low SRP value, so there'll be more oxidation.
Okay, exactly. So among the three reactions, oxidation of sulfate, oxidation of OH minus from water to oxygen, similarly oxidation of copper. So for oxidation of copper, it is having very low SRP, that means high SOP. So what is the preferable reaction? It is oxidation of the copper. Therefore, I can say Cu gets oxidized to Cu2 plus at anode due to low SR. So that means what? If you see overall what is happening, Cu2 plus gets reduced at cathode. Cu gets oxidized at anode. That means only copper is reacting, nothing else is reacting. Have you ever come across this particular case in any chapter? It's been done in your college by any chance? I'll represent this.
Purification of copper.
Exactly, refining of copper. Correct, no? So in case of refining of copper, what do? They take both electrodes, anode and cathode, as copper electrode itself. So tell me, which should be, what is this thick rod and thin rod? What is thick rod?
Thick rod is impure copper, sir, and thin rod is that metal or any surface over which pure copper has to be deposited.
This is pure copper. So impure copper and pure copper. A thin sheet of pure copper will be used. Which is anode, which is cathode here?
Anode is impure copper, cathode is pure copper.
Exactly. So cathode. Now, what did we conclude just now? Among so many reactions here, Cu2 plus gets reduced at cathode and Cu2 plus, Cu gets oxidized at anode. So from anode, the Cu is getting oxidized to Cu2 plus. It dissolves into the solution. At cathode, the same amount of Cu2 plus whichever is dissolved will be deposited. So the process continues. Copper dissolves from anode and copper deposits at cathode. So after a while, the picture will be reversed. This will be a thin sheet and this will be a thick rod. And meanwhile, non-reactive impurities like gold, platinum, silver, they just accumulate near the anode as anode sludge or anode mud. And reactive impurities, if at all any, they would react in water and dissolve into the water. That's all. This is refining of copper by electrolytic method. And by this, what percentage purity of copper you can get at cathode? Hmm? What percentage of purity? You can up to get 99.7, 99.8% pure. Okay, so fine. We'll conclude finally in aqueous solution. If you use copper electrodes, the copper gets oxidized at anode and dissolves into the solution. The same amount of copper gets reduced, and that means it deposits at cathode by reduction. Okay. Now, the other case too, using non-reactive electrodes like platinum, what would happen? We'll take this. If it is complete, I'll proceed. Case B. Using platinum electrodes. These are termed as unreactive, or you can say non-reactive. Non-reactive electrodes. What would happen? Let's see now. Which are the probable reactions at anode and cathode? At cathode, same thing. There is Cu2 plus ions in the solution. They preferably undergo reduction. No problem. Okay. So we'll take up this. Cu2 plus gets 2 electron reduced to copper. This we know from the previous discussion. Plus 0.34 volt, and water H2 plus 2 OH minus. E naught minus 0.41 volt. Between the two, we know this is high SRP. So therefore, Cu2 plus gets deposited at cathode by reduction. Okay. At anode. Which are the probable reactions at anode? We'll take this. That is 2S442 minus, giving rise to S2O8 2 minus plus 2 electron. E naught plus 1.96 volt. Another 4H plus plus O2 plus 4 electrons, giving rise to plus 1.23 volt. What about the one more reaction that we had written for copper anode? This copper undergoing oxidation to Cu2 plus and dissolved into the solution. That cannot happen. Why? Because we are using platinum electrode and it is non-reactive, noble metal. So the other reaction is not there possible at all because electrodes are platinum. Now, between the two, oxidation of sulfate and oxidation of water to give oxygen. So which would be most probable reaction? So OH is oxidized. So between the two, 1.96 and 1.23, which is the low SRP. This is
Water
low,
dissociation.
Liberation of
mean high SOP. So therefore, H2O gets oxidized to liberate O2 at anode. Okay, so the products obtained: copper deposited at cathode and oxygen liberates at anode. Look at that. So quite different. They compared to this SO4 2 minus ion, the oxygen can move relatively faster. Between SO4 and O2, there is no over voltage concept. Whereas between the O2 liberation and the Cl2 liberation in sodium chloride, and their OH minus mobility is far less when compared to Cl minus. So their over voltage concept comes. Okay. So here both are slow. Therefore, whichever has low SRP gets liberated. That's all. Is that okay? So this is one case. We have one more factor to consider to decide products of electrolysis, which are all the things we have seen. Now in molten state, whichever is the ion present, that gets precipitated. No problem. Because in molten state, other ions of the solvent medium wouldn't be there. Whereas in aqueous medium, keeping water as solvent, we need to consider H plus and OH minus ions present also, and then decide the product. So whenever there is a mixture of cations and anions, SRP values are used. For reduction of cations at cathode, high SRP cation will be preferably reduced. For oxidation of anions at anode, low SRP, meaning high SOP, anion will be preferably oxidized at anode. Okay. So in between, if electrodes are reactive, and the reaction of that particular electrode also must be considered, because they are reactive, they can take part in the reaction. Whereas if electrodes are non-reactive, only ions in the solution must be considered for oxidation and reduction to be decided. Okay. And in some cases, the concentration of the ion present in the solution also matters. So for that, I would take one particular case. Okay, concentration. This we have had 3, 4. See, when you take, for example, electrolysis of dilute H2SO4. Okay, let us not complicate it. Say using non-reactive electrodes. Okay, using non-reactive electrodes like that. Now we know this H2SO4 can dissociate to give H plus and SO4 minus. And water, same thing. Now there is no ambiguity with respect to cations because it is same OH plus, and there is a question of SO4 2 minus and OH minus, and the electrode also non-reactive we have taken, they will not participate. Okay, so at cathode there is only one reaction, reduction of H plus to hydrogen, so we don't have to worry about it. At cathode, it is H2O giving rise to H2 liberation and 2OH minus. E naught is, as we know, minus 4.1. No need to compare also because there is no different cation, no problem. So therefore H2 liberates. at cathode. How about at anode? At anode. Which are the two possible reactions? 2SO4 2 minus giving rise to S2O8 2 minus plus 2 electron. E naught we know it is plus 1.96 volt. And another one is the liberation of oxygen. Two, 3 volt. Now, as of now, based on these values, we have just decided also before, this is low SRP. So therefore, O2 liberates at anode by the oxidation of H2O. Okay, but if concentration of H2SO4 increases, if concentration of H2SO4 increases, then that is the case where it becomes a different reaction. But if concentration of H2SO4 increases, then oxidation of SO4 2 minus takes place. At anode. Why it is so? Can anybody tell me? Because you know this reason we have discussed. It is in accordance with some equation. I can give you this hint. If concentration of H2SO4 increases, then oxidation of sulfate is preferred over the oxidation of water to liberate oxygen.
That's the question.
So what is Nernst equation? How exactly it is responsible?
E oxide is directly proportional to concentration of SO4 2 minus.
Correct, no? So it is E of cell, E is equal to E naught is plus 0.0591 by N log the concentration of the ion, right? Now is proportional to log of this concentration of ion. Or if you use it for single electrode potential, E is equal to E naught plus 0.0591 divided by N log sulfate. So when sulfate concentration increases, its reduction potential also will become more. Okay, so as a result, the one with concentration high in the solution will tend to undergo reaction than the one with low concentration. So what we can say, if concentration of H2SO4 increases, then oxidation of sulfate takes place at anode than H2O to liberate oxygen. So thus concentration plays important role. Electrode material used in the electrolysis plays important role. And it is obvious that SRP values are determinant factors for oxidation and reduction. So this is about products of electrolysis. Okay, so I think it's already time up. In the next class, we are going to discuss the MCQs for the entire. We have worked out all the numericals based on delta G naught, Nernst equation, everything. So in the next class, we are going to take up MCQs. Fine. We'll meet for the next class. Thank you. Bye-bye.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. I'm going to end the meeting.